Since 1996, just 1 year after the first discovery of an exoplanet around a normal star, astronomers have been dreaming. What might a successor to the Hubble Space Telescope achieve for exoplanets? What mysteries might it reveal? What new discoveries might ensue? But 26 long years of waiting and wondering are finally over. The Hubble successor, JWST, has been in space for almost a year now. The calibration phase is over, the shakedown is done, and JWST is finally getting down to business. Although we're still only a few months into science operations, I know that many of you are keen to know what is it that JWST has discovered already. Indeed, it was the top-rated video topic from our last poll. So, whilst it's still early days, today we are going to explore what is it that Exoplanet Hub astronomers have found using our new $10 billion toy. Before we get into the science, we first need to orient ourselves with a timeline of JWST. The 6.5 meter telescope was launched on December 25th last year and has spent 6 months in commissioning, which entailed orbital positioning, mirror alignment, instrument calibration, and performance testing. Somewhat concerningly, during this time, at least 19 meteors struck the primary mirror. Of these, one was particularly large that hit around May 24th, and it caused noticeable damage to one of the 18 hexagonal mirrors. Although, fortunately, telescope performance appears unaffected. After 6 months of commissioning, NASA was finally ready to share some of the first images from JWST. So to this end, the telescope took a short series of observations, really just designed to show off the telescope for public outreach purposes, formerly known as ERO, the Early Release Observations. So I bet many of you probably already saw these, the galaxy cluster SMACS 0723, Stephan's Quintet, the Carina Nebula, and the Southern Ring Nebula. Magnificent, spellbinding images that are gorgeous to behold. But alongside these, taken on the 21st of June, JWST observed the transiting exoplanet WSP-96b, a prototypical hot Jupiter-type world. By observing the same transit but at multiple different wavelengths using the nearest instrument on board, we obtain a spectrum of the atmosphere revealing the telltale signature of water, a detection that was announced on July 12th. Astronomers were definitely very excited to see those first ERO images. Like everyone else, our jaws drop seeing those gorgeous panoramas for the first time. But it has to be said that from an astrophysics perspective, we really didn't learn that much. For example, we already knew that WSP-96b had water vapor in its atmosphere from Hubble data that was taken years prior. For us, the really exciting part was actually nerding out on the engineering data about the performance of the telescope itself. On the same day that NASA dropped those first images, JWST project scientist Jane Rigby and colleagues published a paper detailing the performance of the telescope's commissioning phase. For example, a transit of another exoplanet, HAT-P14b, clearly shows an example of what's being dubbed a mirror tilt event. What's happening here is that one of JWST's hexagonal mirrors just unexpectedly changed position, disturbing the time series and creating this bump effect. For astronomers like me that look for exomoons, this is crucial to know about, because if you didn't account for this effect, then you might erroneously think that that little bump up was in fact caused by an exomoon that was exiting transit ahead of the planet. That's exactly the kind of signal that we look for all of the time. This mirror tilting is currently thought to be triggered by a buildup of microstresses within the backplane structure. Worryingly, these tilt events were happening several times a day around April 2022, but appear to have settled down to occurring just several times per month by June. Some more reassuring news here is that already there's been a tool developed that can exploit the phase coherence of JWST's combined light to precisely identify when and where these tilt events occur. Another concern that commissioning has revealed is so-called 1/f noise, which manifests as a kind of banded structure in JWST's spectral images. It appears as though this noise is actually being spuriously injected into the pixel detector by the device designed to read the pixel array, known as the Sidecar ASIC system. Now, it looks like there might be some ways to correct for this in part during post-processing using a technique known as row-by-row odd-even amplifier correction, or ROBA for short. Both the tilt and 1/f noise are small effects, and already we're seeing tools developed to mitigate them, so I'm not too worried about these. But anyone trying to push JWST to its limits will certainly need to adopt analysis techniques to deal with these effects. With the commissioning and the ERO out of the way, in the early summer of 2022, JWST began its first real science operations, known as the Early Release Science, or ERS. Boy, do astronomers love their acronyms. ERS was a DD, which means Director Discretionary Program, which, as the name suggests, means that the telescope time was allocated at the director's discretion, Greg Robinson. This is in contrast to the more conventional format of a committee of astronomers weighing in, known as a TAC, a Time Allocation Committee. The goal of ERS was to try and observe a wide range of phenomena with all the different instrument modes to get a sense as to the science performance. It was largely meant as a community education program, just get some data out to astronomers as soon as possible so they can figure out how to process it all. So ERS was never designed to push the envelope scientifically, but nevertheless, the ridiculous precision of JWST means that some awesome science has already emerged. In fact, the ERS program has just finished wrapping up its observations, and although all of the data has not yet been analyzed, let's have a look at what has been found so far. Astronomy can be split into a bunch of different fields, but today we're just looking at exoplanets. I mean, let's face it, they're the most interesting. Within exoplanets, 2 ERS programs were approved. One, led by Natalie Batalha, focused on transiting exoplanets, and the other by Sasha Hinckley, focused on direct imaging of exoplanets. So 2 very different techniques for studying planets, and indeed the types of planets they typically look at. Let's start with the transit program, which you can also think of as eclipsing planets, one of the techniques we here in the Cool Worlds Lab often make use of. In total, 4 different instruments were used here to study 3 different exoplanets: WASP-18b, WASP-39b, and WASP-43b. As with WASP-96b from the ERO program, these are classic hot Jupiter exoplanets, essentially the easiest type of planet that an exoplanet astronomer could possibly hope for. JWST will eventually push the envelope, trust me, but that is not the point of the ERS program. The spectra obtained for these are gorgeous, and WASP-39b stole the show in August this year when just a portion of the spectrum was published, revealing the unambiguous signal of carbon dioxide, shown here by the increased absorption at 4.3 microns. Now, whilst there has been hints of this molecule and other exoplanetary spectra in the past, this is the first real slam dunk detection of this molecule. The significance is a staggering 26 sigma, for goodness sake. Yet more, we are hearing that in those yet unseen and unpublished portions of the spectrum, there are even more surprises, so stay tuned. In fact, as we were editing this video, what do you know, the team released the other portions showing the detection of carbon dioxide in the other bands, but also found carbon monoxide, water vapor, and sulfur dioxide. Sulfur dioxide is particularly neat, predicted years ago by Kevin Zandler and colleagues, and is thought to form through a series of photochemical reactions of hydrogen sulfide in the upper atmosphere. Looking at the transit light curves, well, they appear almost noiseless. Such is the quality of the JWST data. Now, as beautiful as those transits might look to an astronomer's eye, I can appreciate that they're not quite as visually captivating as, say, the deep field image that was dropped during the ERO. So let's now switch from exoplanet transits to exoplanet imaging, because at least here we have some real photos to look at. The ERS imaging program picked on 2 previously discovered exoplanets. Those were HIP 65426b and VHS 1256b. And it observed a third star that had a known protoplanetary disk around it. That was HD 141569. Let's focus on HIP 65426b, a planet discovered fairly recently in 2017 using the Very Large Telescope. The host star is 385 light years from Earth and has clear evidence for an exoplanet around it on a distant orbit, roughly 90 times wider than Earth's orbit around the Sun. Now you can see in this image that the planet is pretty bright, it's luminous, and that means that it must be a young planet that has only recently formed. Using JWST's coronagraph, light from the host star is heavily suppressed to tease out the relatively dim light from the planet by itself. The team were able to observe the planet in multiple different modes corresponding to different colors of light, and they recover the planet easily in every case. Let me just emphasize, these are the first JWST images of an exoplanet. What's amazing is that the longest wavelengths used here are 11 and 15 microns, making this the first detection of an imaged exoplanet beyond 5 microns. Going a step further and comparing the brightness of the planet as a function of wavelength to theoretical models, the mass of the planet can be inferred and is pinned down here to be around 7 Jupiter masses. The ERS program has now finished, all the data is in the can, but only a fraction of it has been analyzed so far. But even as we speak, JWST is moving into its Cycle 1 observing mode, which means that it's following the more conventional TAC process of assigning telescope time. So that means that astronomers like myself write proposals as to what JWST should look at, and then a committee of astronomers come together, argue about which proposals are the most exciting and thus should be given telescope time. Now this is in contrast to how Kepler, TESS or Gaia operate. Those are survey missions using standardized pre-programmed observing plans spanning multiple years. But this isn't as easy as it sounds. For Cycle 1, the number of requested hours exceeded the available hours by a factor of 4.1, so the majority of proposals were rejected. Cycle 1 will definitely push the envelope a bit more than ERS, but I think it's Cycle 2, which of course follows Cycle 1, where the gloves will come off and JWST can finally start getting into the kind of ambitious science that we've long dreamed of. In my team, that's really what we're looking forward to. The call for Cycle 2 proposals has just been announced, and indeed we are planning some exciting programs to look for exomoons. In fact, based off the early data that we have already, we are able to say that JWST is the first telescope ever built by humanity that is capable of detecting exomoons analogous to the moons that we have in our solar system. Moons like Ganymede, Titan, and the Moon. We know that these things are common in our backyard, so it's incredibly exciting that we might finally have a telescope that could reveal such worlds from many light years away. And on top of exomoons, there's many other exciting targets, of course. One of my personal favorites is the 7-planet TRAPPIST-1 system, which has already been approved for Cycle 1 observations. Unfortunately for exomoons, Cycle 2 won't start until late 2023 and will finish a year later, so it's going to be a while before we actually get that data in hand, even if the TAC agrees with us that exomoons are interesting to go after. The exoplanet transit community has been largely prioritizing studying atmospheres these days, so we know it's going to be tough to persuade them that exomoons are worth JWST's time as well. But I have never been more optimistic about the future. With JWST, we can finally answer questions that have simply been impossible to tackle until now. So let me know, what kind of JWST exoplanet science are you most excited about? Planet imaging, atmosphere retrievals, exomoons, or maybe something else altogether? And of course, that is just exoplanets, just a fraction of the exciting agenda that JWST has in store for us. So look out for an exciting future of new astronomical discoveries, everyone. And until next time, stay thoughtful and stay curious. Thank you so much for watching, everybody. I hope you enjoyed this video. If you did, be sure to like, share, subscribe. And if you really want to help us out, you can become a donor to my research team, the Coolwoods Lab at Columbia University. This week, I want to thank Nathan Forbes, one of our longtime supporters, who has just re-upped his commitment. So thank you so much, Method. All right, everyone, have a cosmically awesome day out there.